Hey, hello everyone. This is Ranjit. Welcome to my video on physical design flow. So to give a quick introduction on what is physical design flow is where when you write your RTL or when the netlist is available, right? You convert into GDS, okay, with certain rules. Okay, they call it as DRC rules. Okay, so this is where the physical design fits in. Okay, it bridges between the logical design. Okay, I have designed the logic to manufacturing. That is the GDS format. Okay, here we do this will impact performance, power, silicon area, utilization, everything. Okay, so now let's go into each step in physical design flow. Okay, physical design flow in VLSI. What are the different flows? First is floor planning. Okay, now we need to see what is floor planning. Floor planning has couple of or floor planning is done in couple of stages. One is when you have your hierarchical block. Okay, you do a chip level floor planning or partitioning, they call it as. Okay, once that is done and pushed into a block. Okay, the block inside the block you do block level floor planning. Okay, now I am going to cover this block level floor planning. What are the different steps in block level floor planning? The first one is estimating the size of the floor plan. Your X and Y axis you need to give, or you need to give the utilization for that block, or there may be different sites. Okay, you may have 5, 6, 7, 8, or different sites. How many sites you are specifying? How do you specify the channels? Many of these sites, right, may be pushed down from the top level. Very few people does it in block level. Block level generally, when there is a rectangular floor plan, we do it. A rectilinear is always pushed. Okay. So the first step after you get your floor plan, right? Your the sizes available. Now it is the macro placement. Okay, macro placement, there are a lot of constraints for macro placement. For example, few of the macros or memories will be sitting together, or it should be sitting near the pins. Okay, so we do pin placement also here. Okay, so the pins are placed, then the macro is placed. uh, then we always do whether between two macros whether there is need for a channel, because the macro pins are there, right? We need to route those, so we estimate the congestion and timing for those macro pins also. Okay, then power structures. Okay, what are the different power structures we have? Different companies have their own power structure, which layer they do the power structure, how dense the power structure is, what is the set to set distances, etc. But mostly that is defined by the flow. Okay, next is physical cell placement. So there are few physical cells also which is getting placed on the stage, like well taps or boundary cells and stuff like that. Okay, well taps generally it is used to power your the NRP wells, right? And your boundary cells mostly it is used to we put it near the maybe a power boundary. Okay, when you jump from one power domain to other power domain, you need these boundary cells or stop cells. Okay, it will stop the continuity of the well taps. So these are some of the physical cell placement which we do. Okay, and the next step is placement. Okay, so this is where your actual standard cells or logics are getting placed properly. Okay, with certain DRC rules. Okay, these we need to make sure these cells are not overlapping. Okay, and are legally proper and sitting in a proper row. Okay, so why do you want to place it in proper row? Very simple. If you place it in proper row, then it will be easy for you to tap the power for these logic cells. Okay, then next step in the placement is to you do optimization. Okay, you maybe you do buffering, for the data path, okay, or you may do sizing of those logic cells or pin swapping, etc. This is called optimization. Okay, so optimization we do for a couple of reasons. One is for getting better timing and getting better power. Okay, power closure. These are the two things which we do, and the main thing or important thing which we take care in placement is to control how the congestion in the area and the utilization as well. Okay, so different companies have their own utilization targets. Some people have 60%, 70%. Some people go more than 70% also for their utilizations. And congestion, as how the tool vendor specifies, right? There are you need to have congestion as much as less as possible. Okay, and next stage is clock tree synthesis. Okay, why do we do clock tree synthesis? Very simple. We need to clock all the registers and macros or memories, right? That is the reason we do clock tree synthesis. The clock source, right? We have defined the clock source in the block, right? Maybe it is entering from the other partition, or this block has a PLL. From that PLL to your leaf pin, right? The registers or memories, you should have the or you should have the clock coming with certain latencies. Okay, that is why we build those clock tree structures. Okay, latencies are nothing but delays. Then the skews. Okay, so when there are interaction between these flops, right? Uh, there are certain constraints where the clock to both the registers or the register and the memory should come within certain time. Okay, then only we can meet the timing constraints. Okay. Also, we will do LDRC or DRV fixing here. What does it means is to actually LDRC and DRC we are doing it to meet the transition targets. Very simple. Okay. If the transition targets are not met, then the clocks will be very slow, and it will have a lot of issues like duty cycle problem, all those jitter issues, all those. Okay. Uh, and yeah, and one more important step in this process is clock routing. Okay, this is the place where these clock paths are routed. Before that, all we do with either virtual routes or global routes. These are estimations. Now it is the actual route which is getting in place. Okay, and and also, when we are doing your actual route, you have the NDRs also will be specified. Okay, whether how the clock path should look like. It should have double width. The spacing between these two clock paths or the data path which will be coming, or if you want some shields, we will do the shields. All those will be taken care here. Some of the examples of complex or advanced clock structuring is like H tree structures. H tree is just the tree will look like a H. Okay, the alphabet H. Why do we do it? We will get a better skew here. Okay, that's why H tree is there. And multi-source CTS nowadays the high frequency circuits multi-source CTS is very common. Instead of one single source, we have multiple sources so that the latency and the skew will be reduced. That is a target for MSCTS. And some more designs will have other kind of clock structures like fishbone structures and stuff like that. Okay. Next is routing. Okay. What does routing does? Routing is where actual routes for the data path is done. Why do we do this? Okay, we want the actual RCE for these structures. Earlier, it is just an estimation we do. Okay, either from the virtual clock, as I said, right, either from virtual clock or global route, where only we define the G cells and what is the congestion for the G cells. We estimate how many routes the G cells can handle. But now, when the routes are there, that is where your what is your crosstalk will come into picture, or your cross coupling will come into picture, because between two routes there will be some spacing. and when some signals, right, changes from 0 to 1 or 1 to 0, it impacts the nearby signals. Okay, this is called crosstalk. Some of the to reduce, see, actually routing is nothing but your RC delays, right? To reduce the RC delays for particularly the vias, some people use via ladder structures. Okay, this will reduce the resistance for the vias. Next is the so once routing is done, maybe in the later nodes, right? People have these DFM steps. Okay, this is called design for manufacturability, where the general DFM step is like the filler cells are inserted, decaps are inserted. Decap cells are the one which will help you to reduce your power glitches. Okay, and they also do metal fill. Metal density is there is a rule in your foundry, maybe TSMC or Global Foundries or Samsung Foundries. They say this much minimum density of metal is needed in these layers. So metal fill is also done in this stage. Okay, so after routing, the actual design is completed. We can generate the GDS or OSS file and we can provide it to Foundry. Okay, next is sign off. Okay, you can ask me one question. Now, once it is routed, will we directly take it to take the GDS and provide to Foundry? My answer is no, because see, I have designed it. Now I need to test whether the design will work at a certain frequency I have designed. Okay, or logically, okay, whatever I have implemented is physically right. Okay, so these are the things which we will do in the sign off. Okay, where we sign off to meet the spec. Okay, it may be a timing sign off to meet the frequency, power sign off to meet the power target, or maybe to meet the IR drop and EM. And physical sign off. Okay, the foundry has some rules for manufacturing it. Okay, the DRC, LVS, antenna checks, those things are done. And the last but not the least is like we also do the logic equivalent check. Okay, because logically and physically it should the functionality should be same. Okay, this is what this LEC or logic equivalent check does. Okay, so these are the steps which we follow it in physical design flow. Okay, 5 steps, right? 5-step process. Okay, maybe details I will give you in next video on these steps. Okay. Before we conclude, let me put a few thoughts to you on the industry practices for these applications, okay, or modern tool practices. Generally, right, the modern tools, right, will have certain things, okay, certain things which will be implemented. First thing is the EDA tool. Generally, for when you design, right, we design multi-million or now it is billions of logic cells are sitting. Okay, so these cannot be hand placed. So we need a EDA tool. Now industry standard tools are like Synopsys, Cadence, and Mentor. Okay, there are some open source tools also available, but it is not currently used in industry. It is only for study purpose people use it. Where we these tools will be helpful for your schematic capture, simulation, layout, and layout verification, all those. Okay. Next is the HDL, your hardware descriptive language. Um, HDL is like it may be your Verilog or VHDL, right? Where the behavior codes are written, or your RDL is written, right? So we use HDL for it. Then design for testability. DFT is a very important one here. Okay, we design some circuits inside the design, whatever we do it for testing it. What are those circuits? It may be a scan chain, it may be a built-in self-test BIST, they call it as, or boundary scan. So this will help before or after manufacturing to test whether these circuits are working properly, or to see if the particular block or particular chip is not working, where is the problem. So we need to debug it, right? So this DFT will help for testing. Okay, it is testability and your controllability. Okay, next is the as I said, right, the physical design tools which we have touch base. This is basically the EDA. Then some of the techniques people use for low power designing, okay, like clock gating, power gating, multi voltage domain, okay, dynamic voltage scaling, DVFS. Okay, these are some of the things which is used common in the industry. Okay, so these are some of the steps, okay, which are the practices which we do it in the industry. Okay, so that's it. My presentation is okay. We'll see you in the next video. Thank you. Bye.